Hello, welcome everybody to a discussion that we're going to be having on this topic of calculus, where I like to call this whole topic as calculus tools because that's really what everything you'll be learning in this course will be applicable on this particular problem. Okay, so the way we're going to work on this is I'm going to try to explain you and walk you through the dynamics of how we choose, critical points, inflection points, the concavity, interval of increase, decrease, and how we analyze functions on even open domain or closed domain with this particular example. Okay, this should be a relatively short video focused towards the example. If you have any questions, please feel free to reach out to me. I'll be more than happy to explain it to you. Okay, so I'm going to try to diversify some things that you already know about this function and the things that you need to know in this course and how to analyze them. Okay, so let's begin. I'm going to try to divide this into a topic of precalculus. Most of you guys already know. And then I'm going to try to talk about what calculus is going to add on to that. Okay. So if you guys already know, this function looks like a very simple cubic. And a cubic function with no further information means that you're just trying to analyze this cubic function all over its respective domain. So as speaking of that, precalculus helps you determine the domain, the range of this function. Okay. As a polynomial of degree 3, a cubic polynomial has a domain of all real numbers and has a range of all near numbers too. Okay, so don't really worry about that. That's something that you're supposed to know from the background of looking at this function. So you should be able to, figure out the domain and the range of the function. The second thing you should be able to figure out is important points. Okay, and important points would be intercepts, both x and y. Okay, that's basically where does this graph cut or touch the x-axis, and where does this graph cut or touch the y-axis. Okay, this is good for visualizing the graph and drawing them, but you should need to know that, how to find them. I'm not going to cover that in this particular video. Okay, if you have questions, just reach out to me. Third thing that you might know is called asymptotes. Okay, both vertical and horizontal if the function has any. Because this is a third degree polynomial, this will probably not have any of those. Okay, so that's the stuff that you should know before entering this into this function, right? So for calculus part, what we have to do is we're going to add up into 2 points. So first of all, we're going to see the nature and extremas. Okay, calculus was going to add those things. We're going to find the nature of the function, it's increasing or decreasing. And then we're going to find the extremas. Does it have a maximum value, a minimum value, here or there, whatever? That's what calculus has to add on to. That's the first aspect of it. The other aspect of what calculus is going to add is the shape. Okay, the shape of a function would mean the concavity of it. Okay, so we're going to try to understand the calculus needs to answer these two questions about this function. Okay, the nature of this function, which means finding the extremas of this, and then the concavity of this whole curve. How does shape? Is it concaving up, concaving down? What's going on? So that's what calculus is going to do. Okay, in this case, we're going to use the derivatives to help us out. Okay, the first derivative is going to help us decipher some things about this function. Okay, always remember in this analysis, whenever you're trying to analyze, you're analyzing the objective function. Okay, you're using the first derivative and the second derivative, and in just a second I'm going to tell you. You're going to use those things as tools to help you give information about this guy. Okay, you're not trying to find the value of the derivative if the derivative is increasing or whatever's happening to the second derivative. We're not looking for those things until and unless specified in the problem. By default, you're working to figure out the nature of this function, and these tests or these tools are going to help you figure that out. Okay, so the first derivative would give you a few things. Okay, first derivative will give you critical points. Okay, to figure out a critical point, you will use first derivative. I'll show you how to do that in just a second. It will give you intervals of increase and decreasing behavior. Okay, It will give you those intervals. That's what the first derivative is going to give us. Okay. Adding on to that behavior, second derivative will give you the information that we're going to call inflection points. I'm going to define an inflection point and a critical point in just a second, okay? So don't worry about that. Those are going to be the given points from second derivative. And then apart from that, it will give you the intervals of concave up or down. Okay? That's a basic shape idea how we're going to be able to define those things. So given this information that we're going to work on a critical point, intervals of increase, decrease from the first derivative, and inflection point and intervals of concave up or down from the second derivative, we can begin and start analyzing this function that we have here. Okay. Before we get in there, I'm going to specify what critical points are. Remember, if you're defining a function of a function f of x, they are the x values where your derivative of x is either 0 or does not exist. Okay, that's the plain definition. We're going to elaborate more on that as soon as we go further. Okay, and then inflection point of f of x. Remember how I'm always putting emphasis on f of x. Okay, are the point. So they're not just the x value. Inflection point is a point. Okay, so for a point you need both x and y coordinate. Keep that in mind. Okay, it's a point where function changes concavity. You gotta understand how they're defined and different. Most of you guys already know that you might just substitute f double prime of x as 0 and find those x values to find the inflection points, but the inflection point is specifically a point where the function changes concavity. Okay, so now adding on to that, possible points of inflection are where second derivative of the function is 0. Okay, so like in the first part, if your derivative is 0 or not defined, done. That x value is a critical point, no problem. Okay, but if you find points where your f double prime is 0, or I should add into this, or does not exist, if you have such points, it is not necessary for them to be inflection points. Okay, for it to be an inflection point, it must implement a change in concavity. Okay, we can test that as we go, as we progress on the examples, but just want to make sure these definitions are everybody's clear on and we're on the same page. Okay, so now I want to talk about basic nature of a function, where we're going to talk about what does a function being increasing mean. A function f of x is increasing, okay, if f prime of x is positive. As simple as that. And where do you want to talk about it? You can talk about a function being increasing at a point, but that's not usually what we're working with. Okay, we're more interested in finding in an interval. Okay, we want to be more in short about if a function is increasing in an interval or not, because at a point you have so many points in a domain. You know, it's going to be crazy testing all of these points to check if the derivative is positive at those points, and you can conclude what's happening. What we're trying to do is we're going to try to decide in nature after I finish up explaining this. Okay, so f of x is termed increasing if, you know, in a particular point or interval, f prime of x is positive. Okay, and a function is deemed decreasing, as you guessed, in an interval or a point if the derivative is negative. Okay, and we know the points where f prime of x is 0 are called critical points, right? So now from common sense, try to understand this. Well, the derivative has three options to be, okay? A derivative can be positive, a derivative can be negative, or a derivative can be zero, right? And now you got to understand, for a derivative to change its behavior from going from increasing to decreasing, it has to change its sign from positive to being negative, right? And that could only happen if it passes through zero, okay? So now the fact that I want to mention is the endpoints of intervals, okay, that you decide where you want to test, are going to be critical points. Okay, so let's say if a function has a critical point at x equals to 1 and at x equals to 2, okay, you will take the whole interval from minus infinity all the way to infinity and put these points here too. So these points are the points where you're going to mark their interval. This is going to be your interval 1. This is going to be interval 2. And that's going to be interval 3. The reason why we're confident in saying that these are the only possible intervals is because if you found out the critical points, you found out the points where the derivative is 0, right? So if you found out these points, the crossing of the nature from increasing to decreasing happens around these points, before or after this point, right? So we're pretty sure that in this single interval, the function is going to be either increasing or decreasing, singular behavior, okay? And then the next behavior will come after the zero crossing has happened at 1, okay? Even if it's going to change or not, we will not decide on that, but the nature will happen later on, okay? So this is the example where I wanted to make sure that everybody understands what's going on, okay? That's the nature of the function. So that's the first part of the derivative that we're talking about. Now let's try to apply this knowledge on this objective function and see what we get, okay? Just the increasing decreasing knowledge. So if my function is x cubed minus 5x squared plus 8x and plus 1, okay? I want to find out whether this function is increasing or decreasing in any given interval. How do I do that? Is by first of all finding those intervals where I'm interested in doing the analysis. And that would mean I want to find the critical points. By definition, critical points are the points where the derivative is 0 or not defined, so we have to find the derivative. Let's do that first. The derivative of this function is very easy. I'm not going to explain how I got that, but you guys can pretty much follow why this is going to be this number. Okay, I got this derivative. Now to find the critical points, I'm going to use CP as a short form of that. To find critical points, all we got to do is set f prime of x equals to 0 and solve for x. Okay, let's do that. So when you set 3x squared minus 10x plus 8 equals to 0, you can factor this quadratic into 3x squared which further will give you 3x minus 4 with an x minus 2. Okay, we have it in this format. So that means there are two possible values. We're going to call them x1 and x2. Where x1 would be coming from this, which is 4 over 3. And x2 is just going to be 2. So these are the two possible critical points that we have. Okay, now because we have the critical points, we can easily identify our intervals. If I put a number line down there, I could have intervals ranging from negative infinity to positive infinity, breaking them up at 4 over 3 and 2. Okay, so I have basically 3 intervals. I'm going to write those intervals right now in the bottom so you can see what I'm talking about. The first interval is from negative infinity all the way up to 4 over 3. The second interval is from 4 over 3 all the way to 2. And then the last interval is from 2 to infinity. So now I know that in this interval all the way, the function will only have one singular behavior. Okay, it's either going to be increasing or decreasing. I know for sure. in this interval as well, the same thing applies. In this interval as well, the same thing applies. So what we're going to do is we're going to test the behavior of the derivative function in this interval by picking any random point we feel like and try and test them. Okay, so what I'm going to do is I'm going to pick, a random value. I'm going to pick x equals to 0 from here. Okay, because 0 lies in that interval, so I can pick x equals 0. And if I try to evaluate my function's derivative at 0, what do I get? I would get a plus 8. Okay, if that implies that the derivative is positive, that means it's going to stay positive in this whole interval, which would mean the function is going to be increasing in that interval. Easy peasy. Moving on. Now the next step is to pick a point in this interval. Okay, in the second interval. So out of 4 over 3 is like roughly 1.33, right? So if you pick a point between 4 over 3 and 2, I would pick, 1.5 or 3 over 2. If you pick 3 over 2, right, and try to evaluate your derivative at that number, let's see what we get. We're going to get 27 over 4 minus 15 and a plus 8. Okay, so I know this will just be 27 over 4 minus 7, and 27 over 4 is definitely going to be smaller than 7. Okay, so I know that because 28 over 4 will be 7, and 27 over 4 will be less than that, hence making this guy a negative number. Now we know in this second interval, the function's derivative is negative. Now we can say that the function is decreasing in that interval. Okay, moving on. In the last interval, you can pick any point you want. I'm going to pick x equals to 3 and test it. So if you pick x equals to 3, then your derivative at the value 3 is going to be just 3 times 3 squared, 27, minus 30, and plus 8. And this number is going to be bigger than 0. Okay, because this number is bigger than 0, we can say in the last interval, the function is increasing. Okay, that's how we decide whether a function is increasing or decreasing from the value of derivatives. Okay, the value of derivatives has no significance. All we're trying to decipher is what's happening to this objective function. Okay, so don't get carried away by plugging in this. So if you find a critical point and you want to test what's happening to the derivative, you would plug those points that you pick from the intervals in the derivative, because that's what we're interested in. And because of the derivative being positive, negative, we can make conclusions about the objective function's behavior. Okay, increasing or decreasing or increasing in this particular case. Now I want to give you a brief logic behind something we've learned as a first derivative test, and that's going to be used in classifying these points as extremas of max or mins. Okay, so we know that you have critical points, and the critical points are the points where there could be a possibility of an extrema. By extrema, I mean a local max or a local min. So let's try to use a common sense and see what's happening. So we know in this interval from negative infinity to 4 over 3, the function is always increasing. Okay, so the function is going to keep on growing, going up and up and up and all the way. And once it goes up, and now we know the interval right after that is going to start to decrease. So that makes a possibility of having a local max at this value. Okay, why? Because if you see, the function was increasing all the way up to this point, and then it starts to decrease. So that means at this 4 over 3, the value itself has reached the maximum it was supposed to, because it starts to decrease further from there. So you've reached a max. Okay, continuing the same logic here for the value 2, here your function was decreasing, and then right after 2 will start to increase. So it'll keep on decreasing up to the lowest value once at 2, and then start to increase after that. That makes this function as a local min. Okay, I'll tell you why I say local min in just a second, and what's the difference between global and local. That's coming up forward, so don't worry about that. That's literally the analysis that you need to do in order to understand what you get from the first derivative. Okay, so the first derivative gave you the critical points, which are the possible places where you'll have a local max, a local min. And with that being said, you can also classify the intervals for the behavior of the function. Okay, that's how we know that this function is going to have an increasing behavior or decreasing behavior, and you're going to have a max or a min. Okay, so that's the first derivative analysis. Now moving on to the second derivative analysis is where we're going to see the inflection points and concavity. Okay, it's very simple. Again, I'm going to try to show you here. A function is going to have a shape of concave up, which means a shape like this, if the second derivative of the function is positive. Okay, and a function is deemed to be concave down like this if a function second derivative is less than 0. And this could be also analyzed at a point or an interval. Of course, we're more interested in towards talking about the intervals where that happens. Okay, so that's where this is. Now, the point where it changes, okay, if it's concaving up and it starts to concave down from this point onwards, this point is called the inflection point. Okay, again, because the same logic, if a function was concaving up and it's now concaving down, that could only happen if there was a stop in between at 0. Okay, so f double prime x being equals to 0 is going to give you possible inflection point. Okay, that's how we find out what's happening. And now this, as the possible inflection point, will become the point of the end of the interval. Okay, so if you know you want to analyze the function's second derivative here and see what's happening if it's concaving up or down, this number, let's say if a function's at 0, will give you a value at x equals to 2. Okay, let's say at x equals to 2, the second derivative of the function was 0. So if you put down that 2 there, now this becomes your interval 1, and this becomes your interval 2 for the concavity analysis. Okay, this is not for the increasing decreasing behavior, so this is a different interval. Okay, so in interval 1, if you want to try to see if a function was concaving up, that means the second derivative was positive, and then right after that in the second interval, if it started to be negative, then you know this is a valid inflection point. Okay, so to find those candidates, we're going to use the same analysis. Moving on to our example that we did the first analysis here. Now I'm going to move on to see the concavity of this function. So again, objective function right here will be x cubed minus 5x squared plus 8x plus 1. We've found out the derivative of this function, which turned out to be 3x squared minus 10x plus 8. And now we're going to find the second derivative because we're going to use that to analyze the concavity of the objective function. The second derivative is just going to be 6x minus 10. Okay, so now the possible points of inflection, or the endpoints of the concavity domain or analysis interval, will be given by finding the points where this guy is 0. So when you set up 6x minus 10 equals to 0, you get x equals to 10 over 6, or in simple words, 5 over 3. Okay, so now this is the point where there could be a possible inflection. So we'll try to test what is f double prime of x doing around this location. So we have the first interval from negative infinity to positive infinity of this. The interval 1 is from negative infinity to 5 over 3. And interval 2 is 5 over 3 to infinity. So just want to put more emphasis. 5 over 3 is not an inflection point just yet. It's a possible inflection point. Okay, in the previous case when we were trying to find critical points, we definitely know 4 over 3 is a critical point without doing any analysis. Okay, but the analysis of inflection point requires you to check if the inflection actually happens or not. Okay, so let's see that. In the first interval, you're liberty to pick any x value you want in this to evaluate the derivative or second derivative, right? So if I pick x equals to 0 that lies in that interval, and I evaluate my second derivative at 0, I'm going to get negative 10 as a result. So negative 10 implies that my second derivative is negative, which means the function is concave down. I think it's better to write it down there. Okay, so in this interval, the function is concaving down. Very easy. Now moving on to the next part, and we're going to pick a random value of x here. 5/3 is definitely bigger than 1, but smaller than 2. So what I'm going to do is I'm going to try to pick a value x equals to 2. And if you evaluate the behavior of your second derivative at 2, what you're going to get is 12 minus 10, which is 2. Now, since that is positive, we can say the function is concaving up in that interval. Now, because the concavity changes at 5/3, just before 5/3 was concaving down, and after 5/3 concaves up, then you can definitely say this is a valid inflection point. And remember, inflection point is a point. Right now, we only got the x value or the x coordinate of that point. So the inflection point will be 5/3 and the value of the function is 5/3. Okay, this is the coordinate of the point. To find the value of the function of 5/3, you have to plug it in and find that out. Okay, so this is all that we have right now after analyzing this objective function. We know a lot of things. I'm going to move on to the next page and summarize all that information so you guys can have a condensed idea of what we're doing with. Okay, so I'm going to have the function again. Cube minus 5x squared plus 8x plus 1. Okay, from the first derivative, okay, the information we got was there are two critical points where x1 is 4/3, x2 is 2. There are two critical points here where we know x1 equals to 4/3 is a local max, and x2 equals to 2 is a local min. Okay, and when we know this, we can always give intervals where it's increasing. The intervals of increase was -infinity to 4/3, and a union. So that's where a lot of people have trouble with. Union is just trying to make sure we combine these two intervals. Okay, the combination of intervals is done with a U sign. It also means union. 2 to infinity, that's where the function is increasing, and the function is decreasing in 4/3 to the 2 of interval. That's the information that we get from the first derivative. The second derivative gave us how it's doing what it's doing. Okay, how is it increasing? What's the curvature like? So it has one inflection point where we're going to call that, x3, because I'm already taking x1, x2. The inflection point is x3. We call that 5/6. Was it 5/6? No, 5/3. My bad. 5/3. That's the inflection point. We have verified that's an inflection point, so I'm going to put a tick there because it's verified. And we have the concavity. So concave up in the interval from 5/3 to infinity, okay? And concave down from the interval of -infinity to 5/3. So this information is all that is given to you using calculus tools, okay? Now we have to interpret this information and try to come up with a sketch of this function, okay? To do that, I want to introduce an extra step, okay? I'm going to make the axes here, and I want to talk about the common sense first, and then we're going to come back and sketch it here, okay? The common sense is if you have a function's derivative positive, and if you have a function's derivative negative, I'm going to put the derivatives in just a second. Okay, derivative positive and derivative negative. Okay, then if you are at a point A and you want to go to point B, you're going to go in an increasing fashion, right? That's what it means for a derivative to be positive. The same thing here, from A to a b value. Okay, I'm going to try to make this into a section so you can segregate the work that I'm talking about. Okay, so now given that idea that we have a to b, we have an increasing behavior. If you have a decreasing behavior like in the bottom two sections, we'll have a value at a on the top and the b value will be below that. Okay, now why do I make these sections? Because a function can have three options in all of these behaviors. The three candidates of how it's going to be increasing or decreasing could be given like this. So the function can just straight up increase from a to b. That's the first way of doing that. It's a constant linear increase. The other way to do that is by this way, where you see this function is basically concaving down in that aspect. Okay, and the last possibility for a function to reach from a to b is going like this. Okay, like in that concave up fashion. So I'm going to make those second categories here too. So now I'm going to have an increasing behavior. So I know f prime of x is positive, increasing behavior with concave up, increasing behavior with concave down, increasing behavior with concave up, and increasing behavior, or decreasing behavior with concave up and decreasing behavior with concave down. Okay, so I'm going to put them down here, increasing concave up. Okay, this is also increasing concave down. Okay. Decreasing but with concave up, and now this is decreasing with concave down, right? So I'm going to try to draw these sections of how they look like. If you have an increasing concaving up, then your curve is going to look like this. That's how it's going to look like if you draw that particular piece of the graph. If you're increasing but you concaving down, your piece is going to look like this. Okay, both of them are increasing from a to b, but they're increasing in different ways. So the curvature is decided by the second derivative. Okay, now we're decreasing and a concave up in the third option. So it still wants to concave up but decrease, so it's going to look like this. Okay, and now you're decreasing and concaving down will look something like this. Okay, so now any sketch of the function could be broken down and made up with these four fundamental pieces. Okay, all you have to do is make sure you classify those intervals, and in each of these intervals you're looking what the function's derivative and second derivative is telling you. Okay, that's why I summarized the data in the part before. So make sure you have this handy. We're going to move on back to the sketch and try to see if you can sketch it. Okay, I'm going to redraw these axes so I can have a better understanding of what's happening. Now I'm going to try to use the blue color to put up the points that I get from the first derivative, and I'm going to use the green color to put up the information I get from the second derivative on the same graph, so you guys can have an understanding of what's going on. Okay, so the first point is x1, which is going to be 4 over 3. The second point is x2, which is going to be the value 2. Okay, that's that. So I know that this function will have a maxima somewhere here and a relative minima somewhere here. Okay, I just roughly made those values. To find those precise values, you will take these points and plug them into the main function, because we're trying to analyze the main function. Okay, again, emphasis on that. So good, that's tough. From precalculus, I know because it's a cubic, it's going to have to extend this way in the very left hand, and it's going to extend that way in the very right hand. Okay, so I know where the graph is headed to and where it's going to start. So that's good, no problem. Now, using the green value, I'm going to put up the 5 over 3 there too, because that's also an important point. 5 over 3, which is x3. Okay, that's an inflection point. So now I'm going to try to make like these intervals and noticeable in a way so I can have this idea. Okay, and extend this all the way down. Extend this all the way down. Extend this all the way down. Okay, So now, if you use these factors to make intervals, you will have a total of 4 intervals. Okay, I'm going to use red for that interval category. Okay, the first interval is right here from negative infinity all the way to 4 over 3. So I'm going to call the interval 1. Then I have this interval, second interval, where it's going to be from 4 over 3 to 5 over 3, which is the inflection point. This will be the third interval, and this will be the fourth interval. Okay, so now we have to identify the nature of both the functions and its derivative, okay, in this 1, 2, 3, 4 intervals. Okay, so I can use these pieces to draw the graph. In the first interval, I know, because this first interval overlaps with this guy here, right? That's the first interval in the red. So I know that my f prime of x, try to draw it in the bottom so I don't miss out on that. Okay, so now if I zoom in here, so I know my f prime of x is positive in that interval. And now, if you see that, that's also the interval of overlap here with the green function. Oh no, not this one, the other one. From negative infinity to 5 over 3, right? So in that interval, my second derivative is going to be negative, so it's concaving down. So the first interval, my function is going to be having an increasing behavior concaving down. So it's going to be this piece. So that's how I'm going to draw the graph here. Okay, I'm going to take this this piece here, and I'm going to try to draw from here all the way to here. Okay, that's the piece. So this piece is increasing but concaving down. Okay, let's move on to interval 2. Interval 2 in the red here, I know my behavior of the function changes because this interval in the red will lie here. This is 4 over 3 and 2. So I know in this particular zone, my function's derivative is now negative, but my second derivative is still positive. So in that interval, I know my function is going to be decreasing, but still concaving up. Okay, so I'm going to put a midpoint here so I can kind of like draw that piece there. Okay, so my function will be decreasing, but concaving up. So the graph will look something like this. This is the piece. Hold up. No. I'm messing it up here. Okay, gotta go now. This is still the interval where it's concaving down. My bad. I caught it in time. So that will be 0, less than 0. So now the function is decreasing and concaving down. Okay, so the piece of the graph will look something like this. Okay, I'm trying to exaggerate these figures, but I'm just trying to make sure you understand how the pieces are placed. And then I'm going to draw a smooth sketch later on. Okay, so with that being said, that's interval 2. For interval 3, okay, you got to know that interval 3 is the interval where the function is still decreasing, okay, because it's in between the values of 4 over 3 and 2, but the concavity has changed now. Okay, so here, my first derivative is still 0, so it's less than 0, so it's still decreasing, but my concavity has changed to concaving up. So from there to this point, this will be a function that's decreasing but concaving up, so it still looks like this. Okay. And after that, the last piece of the puzzle is very easy to do because in the last piece, your function will start to increase again. So a function's derivative is positive and the concavity is also positive. So this would mean that you have a function that's concaving up and increasing at the same time. So the piece will look like this. Right, and then I can extend this to infinity what I want. So that's how we kind of understand the graph of it. Even though right now it's not being tested, it will come up eventually in the future. So I want to make sure you guys understand how these graphs look like. So if you were to sketch this thing, you know, in a nice small coherent way without the mess up, it will look something like this. Okay, where you know this is the maxima happening at 4 over 3. This is the minima happening at 2, and this is your inflection point at 5 over 3. Okay, and of course you can put up those values and kind of do that, but I wanted to show you these individual pieces and connecting these dots to make the whole graph. Okay, and this is all that it is there for the analysis using calculus tools. Okay, right now we were trying to find the function's behavior everywhere. Okay, but now the last part of the puzzle is if we ask you to do closed interval analysis, how that changes the picture. Okay, so I'm going to move to the fresh page and show you there. For the closed, oopsie, that's a very skinny pen, so I'm going to closed domain analysis, okay, would mean that you're restricting the values of x that you can choose for the function. So let's say we're going to still stick to the objective function here, okay, and the objective function is still going to be x cubed minus 5x squared plus 8x plus 1. But now I'm only working with x values, let's say from 0 to 10. Okay? If x has to stay between 0 to 10, then we'll have a closed domain analysis. And now, because when you have a closed domain analysis, our minimas or extremas will have two definitions. Okay? Our extremas, both max and min, could be either locals or globals. Okay, because now we have a global context. We have all the possibilities in this particular restriction, so we can classify the most positive value as the global and the relatively positive value as a local, and vice versa for the minimums, right? So that's what we're going to do. How we do this analysis, how is this different from how we would have done for the other case, is you would do the same stuff. You will still find the critical points, but instead of, trying to use logic to identify which critical points are going to be max or min, we just literally find the values of all those things. Okay, so now I know there are two critical points already from the analysis that we did before. x1 being 4/3 and x2 being 2. Okay, and there are two endpoints of this interval. So endpoints are also included in this analysis, where the endpoints are going to be either x3 as 0 and x4 as 10. So I'm just labeling these as values. You don't have to really do that, just to make sure we understand all this. So now the candidates that would have possible extremas are going to be all these four candidates. And now we have to just test the value of the function at all these points. So if I was to test the value of the function at the first critical point, 4/3, I'm going to just plug in 4/3 into the function. Minus 5, that's a cube. 4/3 squared plus 8 times 4/3 and a plus 1. I'm going to find that value in just a second. I'm just going to use a calculator to do that. But that's the first value of the critical point. The function's value of the second critical point, which means that 2, would be 2 cubed minus 5/2 squared plus 8 over times 2 plus 1. I'm going to do that just in a second. I'm going to write the formats first. And for the endpoints, when I plug in the value of 0, the first endpoint, plug in the value 0, I get 1, so that's easy. And then the value of 10, the other endpoint, would mean 10 cubed minus 5 times 10 squared plus 8 times 10 plus 1. So I'm going to try to quickly get through the calculator and get these values for you, and then we can move on with the analysis further. So my function is x cubed 5x squared 8x and minus 1. Oh, my bad. So given that information, the value of the function at 4/3 is going to be about 5.14. Just keep that handy. That's the 5.14 value. Function's value at 2 is literally 5, so that's easy. And the function's value at 10, which is going to be very big, 581. Okay. So now that we have this picture in front of us, which one out of this becomes the global maximum? Okay, because we know we've done the analysis before. We know this was a candidate for local max, right? And this was a candidate for local min, right? So these candidates are still valid, because why would this become local is because there was a value which is below that even there. So this is 1. And that's the smallest value, so this becomes your global min. And that means the other min becomes the local min. Okay, that's the important thing. And here 581 is the biggest value, so that becomes the global max. Here, leaving the other guy to be the local max. Okay, so now that's the idea. Now I just want to clear the air here before we begin and like end the session. The locals in this opinion, okay, could be both given from the critical points and stuff, right? The globals here could be both candidates, okay? So critical points and endpoints both could be globals, okay? But locals can only be critical points, okay? If you have an endpoint and you want to classify it as a local, that's just not possible because the endpoint does not have any locality around it, okay? So just keep that in mind, that if you want to answer for a global maximum, it could be both critical point or endpoints. If you're testing for globals, you need to make sure you're testing both the critical and the endpoints. And if you just want to find the locals, you don't have to do the endpoints analysis at all. You know, the locals are always going to be in critical points. Okay. If a function has a lower value on the endpoint and doesn't want to be a local, then that point is not classified as any extremis. That's just any random point. Okay. But if you need more help with this, I know you're going to be doing OQ questions and you want to make sure you're getting in the assignments and all the things correct, please feel free to reach out to me. Okay. So, excuse me, hopefully this video made sense and we're trying to understand the rules and how we work with these little pieces. I try to work it in an example way form so you guys can understand what's happening. I haven't really talked about the tests to classify the points as a max and a min. The way we did it here is formally known as the first derivative test. Okay. First derivative test is the test that actually helps you find out whether a function is having a max or a min at the critical point. And that's just basically as like this. If you want to find a test 4/3, what you do is you test a point before that and you test a point after that. If the function has a behavior where the derivative was positive, then became negative, then this point is classified as a max. If a function derivative was negative and then it became positive, then that critical point is classified as a min. That's the first derivative test. Okay, there's one more test I want to talk about, and that test is basically the second derivative test. So, second derivative test can also be used to classify a point as a maximum minimum. So again, I want to put the emphasis. We're still working with the objective function f of x, okay? And we're trying to test what? Test the critical points of f of x, okay? Which we got from the first derivative, okay? So we got to make sure everything is in place. So the objective function that we're working with is still x cubed minus 5x squared plus 8x plus 1. We already know the first derivative was 3x squared minus 10x plus 8. And now the second derivative, because to apply the test we need the second derivative. Second derivative here is 6x minus 10. Okay, so we have all these here. So now the candidates that we want to be testing are the critical points. And those were x1 being 4/3, x2 being 2. Okay, these were the two candidates that would have, you know, max and a min, and we just want to identify which one has a max and which one has a min. So to do that, we're going to apply the test. The test is as follows. So if x1 and x2, or you know, if x1 is a critical point, and the second derivative's value at x1 comes out to be less than 0, which implies the function is concaving down at x1, that means x1 would be a max. Okay, because if you have a function that's concaving down and has a critical point, it will have this kind of shape where this automatically becomes the max. Okay, and if x1 is a critical point and your concavity at that critical point x1 is positive, so it's concaving up, that implies that one will be a minima, because if your function is concaving up and has a critical point, it will have a shape like this. That makes the point automatically a minima, right? So that's the test. Now to apply the test on these 2 points, I'm going to try to find the value of the second derivative of the first candidate, 4 over 3. That came out to be 6 times 4 over 3 minus 10. So that would just be 2 times 8, so it's going to be negative 2. Okay. Now because the second derivative is negative 2 at the 4 over 3 value, that means the function is concaving down, making 4 over 3 a max, because that's what we concluded in the first. And if you apply the test on the second candidate, which is 2, if I plug in 2 there, then I'm going to get 12 minus 10, which is going to be positive 2. So that means it's concaving up at x equals to 2, making x equals to 2 a min. Okay, and now the context of it being local or global could be attached later on, after the thing is done. So this is how we do the second derivative test on any function. Just to summarize before we end, you have an objective function. The second derivative test is to test the critical points and classify them as max and mins. The critical points could be found out by finding the first derivative and setting it equals to 0. And then now you plug in those values in the second derivative. If the second derivative at the critical point comes out to be negative, then that point is going to be a maxima. If the second derivative at the point comes out to be positive, then it will be a minima. It's counterintuitive, okay? So make sure you're able to follow along with all these things in order. And hopefully this video helped you out, right? So if you have any questions, you know how to reach out to me. And I'll see you in the next one. Thanks for watching.